Okay, Lesson 7, Calculating Probabilities of Compound Events. What you're going to need for this is a calculator. Alright, so the content of this lesson is deliberately similar to the material in Lesson 6. You are likely to notice this relation to previous material. It is important that tree diagrams be used to effectively map out a sample space and to compute probabilities no matter how many stages or outcomes the situation has. So let's take a look at example 1. We'll take a look at a couple of scenarios and see how we can use a tree diagram to illustrate these. How about decorating a house? A designer has 3 different paints to use for the client's house: red, white, and blue. The designer is responsible for decorating 2 rooms of the house, the kitchen and the home office. If each room is expected to be a different color, how could a tree diagram be used to organize the possible outcomes of what color each room is painted? Well, you could set it up like this. Let's say the kitchen is the first stage. Well, the kitchen can either be red, white, or blue. Well, then the second stage would be the office. And for each of the office choices, it could be red, white, or blue. So the combinations, if the kitchen is red, then the office could be red also. So the outcome is red, red. Or red kitchen, white office, or red kitchen, blue office. And same thing for if the kitchen is white and if the kitchen is blue. You have the same 3 options. And here are our outcomes. How about organizing a school schedule? Consider the following possible scheduling problem. Ralph needs to select courses for 2 hours of his school day. Possible courses he can take are music, science, and mathematics. Each course is offered during the first and second hours of the school day. How could a tree diagram be used to organize the possible outcomes of Ralph's schedule for the 2 hours? Well, again, the first period, you'd either have a choice of music, science, or math. And for the second stage, or the second period, you have the same 3 choices. So then your outcomes could be music, 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 science, and music, math, which wouldn't really make sense, but still, when you can list all the possible outcomes, you still need to consider that music, music is an outcome based on the information that we're given. The same thing for science and math, you would list all 3 outcomes. So the total possible outcomes are here, even though some of these might not be realistic. Recall a previous example where a family decides to play a game each night, and they all agree to use a tetrahedral die, that 4-sided die in the shape of a pyramid, where each of the 4 possible outcomes is equally likely. Each night to randomly determine if the game will be a board game or a card game. The tree diagram mapping the possible overall outcomes over 2 consecutive nights was as follows. You can find this in your math journal or in the previous lesson notes. So, but how would a diagram change if you're interested in mapping the possible overall outcomes over 3 consecutive nights? You would need to accommodate this additional 3rd stage. You would need to take steps similar to what you did before, and you would attach all possibilities for the 3rd stage, Wednesday, to each branch of the previous stage, which was Tuesday. And this is what it would look like. So you need to make sure that you spread your first stage out pretty far so that you can accommodate each stage. So after the 2nd stage, we would have to attach an equal outcome, B, board game or card game, to each of the outcomes from Tuesday night. So here your outcome would be board game, board game, board game, and so on and so forth. So some important points to note. The tree diagram is an important way of organizing and visualizing the outcomes. And the tree diagram is particularly useful when the experiment can be thought of as occurring in stages. When the information about probabilities associated with each branch is included, the tree diagram facilitates the computation of the probabilities of possible outcomes. And the basic principles of tree diagrams can apply to situations with more than 2 stages. So let's use this to do exercises 1 through 3. answer the questions, and continue the video to check your answers. Alright, so you should be done with exercises 1 through 3. Here are the answers. If you have any questions, make a note and bring them to class. Alright, so let's take a look at example 2. Read the problem set up on your lesson worksheet. We're now going to add the probabilities to the tree diagram. So this was a continuation of the problem from lesson 6. Now we have our added probabilities of 75 hundredths and 25 hundredths to each of the third stage. Now you need to go ahead and continue to multiply these together to get our probabilities for each outcome. 2 of them have been done for you. You need to do the rest. Alright, so what does CBC represent? Well, CBC represents the following sequence: card game the first night, board game the second night, and card game the third night. The probability of CBC is approximately 0.046785. What does that probability mean? Well, the probability of CBC is very small. This means that the outcome of CBC is not expected to happen very often, only about 4.5% of the time. So although it's not impossible, it is definitely unlikely. Alright, try exercises 4 and 5. You may use a calculator to speed up the process and check your answers by continuing the video. Alright, you should be done with exercises 4 and 5. And here are the answers. Again, make a note if there's anything that is confusing or doesn't come out the way you calculated it. Notice that the sum of probabilities of the 3 outcomes is not 3/8 or 375 thousandths. Why? Well, we previously discussed that outcomes for the 3 nights are not equally likely. So to answer question number 6 and then continue the video. So the probability for the family will play at least 1 night of card games is probably easier to answer by a subtraction problem. 1 minus 0.421875 will give you a probability of 0.578125, or 57.8%. Alright, complete exercises 7 through 10, checking your answer after each one by continuing the video. So here's the answer to number 7. Number 8. Number 9. And number 10. Alright, let's wrap this up. If you knew that a certain game where only the outcomes win or lose offered a 35 hundredths of a chance probability of winning each time, can you calculate the probability of losing such a game 5 consecutive times, given what has been discussed so far? Well, if the chance of winning is 35 hundredths, then the chance of losing a game is 65 hundredths. So the chance of losing 5 games, or 5 times, would be 65 hundredths times 65 hundredths 5 times, or approximately 116 thousandths. Did you need to draw a tree diagram for this question? Why or why not? Well, no, it's not necessary for this particular outcome. When the outcome represents the same event occurring several times, the probability of that outcome is the probability of the event multiplied by itself for each time the event occurred. In this case, it was 65 hundredths times itself 5 times. So what are the chances of winning at least once in those 5 games? Well, if you win at least once, the only outcome you avoided would be losing 5 times. So all other outcomes would be valid, and the sum of all their probabilities would be 1 minus 1.16 or 0.116, which would equal 0.884. So there's actually a good chance you would win at least 1 over 5 games, or about 88%. All right, see you in class.